Welcome to today's webinar on Advanced Surface Editing, a demonstration. My name is Janina Elliott, and I'm the technical lead for Central at Sequence and your host for today. So thank you very much for tuning in. Let's get started. All right, just a little bit of housekeeping first. During this webinar, the audience is muted to ensure that the presentation doesn't run over time. If you do have questions, however, please feel free to use the question window in the GoToWebinar dialog, and I'll make absolutely sure that after the presentation, your question will be answered with a personalized email. The presentation today will utilize the latest versions of Leapfrog Geo 4.3 and Central 2.0. And should you have not had the chance to upgrade to the latest Leapfrog product suite, but are interested in the latest functionality for Geo, Edge, and Central, please feel free to visit our website or drop us a line to request the link for our associated webinar recordings. Okay. This webinar is primarily designed for existing Leapfrog modelers, but also holds valuable information for everyone new to the software suite, of course. A recording of this webinar will be made available to all registered viewers shortly after the presentation. Okay, so what's our agenda for today? For today's webinar, the idea is to introduce the concept of editing in an implicit environment, and to understand why the techniques and tools applied here are different from what we're used to in the traditional sort of often CAD-based software. We have to first illuminate the differences between implicit and explicit modeling softwares. So that's how we're going to get started. Because only once this fundamental sort of paradigm shift is defined, we can then talk about sort of what are the common surface issues experienced in Leapfrog and really understand them, where they stem from, and how we can actively deal with them. At that point, I'm going to jump into a live demo starting in the Central browser, so sort of our natural place for all of our model versions. We'll go from here, identify the correct model that we need to work on, and then we'll jump into Geo, where we'll work on the appropriate surfaces. And I'll demonstrate a number of techniques on a universal example, how you can modify surfaces in the implicit world. Once the surface editing process is completed, we will publish the finalized model back into Central. And finally, I will briefly provide some information on upcoming events here in Vancouver, as well as the upcoming webinar, and provide you with some data on our support team, how you can contact us, and how you can learn more from implicit modeling. And of course, at the very end, I would love for you to participate in a little survey, just a couple of questions that would help us to improve, of course, our next webinar, or overall our work, and and just to provide you with everything that you need. We'll need your participation in that. Okay, let's keep going, and let's have a look at that paradigm shift I just mentioned. Implicit versus explicit modeling, or don't waste your time with polylines. Good God, okay. Most of us that have started their modeling careers in the explicit world will be utterly shocked by such a statement. But in the implicit environment, we don't just wireframe or force a model into a certain interpretation. We work with the data to make the best decisions possible using both statistics and geological expertise. So it is a bit of a different setup that places polylines or manual modification sort of at the end of the process. It's still there, but it's not the starting point. So let me start by explaining exactly what the fundamental differences are between implicit and explicit. Okay. So this slide is a little text heavy, so let me just talk you through it. The principal idea here is that a paradigm shift has occurred in the 3D modeling world. And let's talk about the explicit scenario first. So quite frequently, a modeler in an explicit software program is hit by several major challenges. One, for example, is that explicit software packages such as Vulkan, for example, GEMS, etc., are not particularly intuitive. And it takes quite a few years actually to become truly proficient in those programs. And I personally have a lot of respect for anyone that drives those programs really well and can wireframe extremely well. Commonly in the programs, the geologist has to work in a sort of 2D plus environment where data is heavily restricted to sections, and it's up to the modeler's expertise to interpret how the data is connected in the black spaces in between. This process is called wireframing. And for anyone that doesn't know this particular term, wireframing, the idea is that the modeler has to go through quite a painstaking process to digitize every single data point, and then the modeler has to connect them, so these data points, via strings. These strings are much like polylines that sit on sections, which then are in turn connected in the 3D space to create a volume. So they're extracted into a 3D space to make up a volume. This exercise has to be carried out for each litho unit, and the modeler has to make sure that each volume fits the one next door perfectly to create an airtight model without any intersections. So each volume has to neatly fit next to each other. Now, of course, imagine what happens once new data is added to the model. Basically, the whole process of digitizing on local sections and the interpretation of each individual point relative to the others has to start over again, and not just for the one volume, but basically for all of the adjoining ones as well. And this, of course, results in a ton of work that just takes time. From this perspective, it's not really surprising that explicitly derived models tend to only contain one level of geological interpretation. It may or may not respect or other collected drill data such as structural information, geological, geophysical measurements, etc. Okay, so while the geologist is working really hard to keep up with deadlines and new data, he or she is really heavily limited by the constraints and the complexity of the software, which is truly really a shame because the results are not commonly reflecting the geological know-how of the person sort of driving the model. It's really more of a representation of the modeler's expertise regarding the software itself and the time constraints overall. Okay, so now the explicit software takes a completely different approach to 3D modeling, as it is based on a mathematical evaluation of the data in combination with skilled interpretation. And before some of you scream, black box, well, this whole webinar is designed to show you that it really is not. Leapfrog is not a black box. You have full control to make the changes necessary to develop a true geological interpretation that takes advantage of a statistically sound base model. Okay, so the great news is that it won't take as long to learn the software because it's intuitive and it's created by geologists for geologists. So we have a natural handle on Leapfrog as a software product. In addition, it allows you to integrate more than one data set, that's Leapfrog Geo, and quickly develop several levels of interpretation within one project. Whenever there is a new stream of data coming in, the dynamic link between the data source and the final model allows for your interpretation to be updated instantly without the painstaking process of digitizing every single data point. And therefore, because of the way the software is set up, dynamic linking, etc., modeling becomes a really objective exercise and the models are reproducible. Okay, which allows, of course, for a very clear and auditable reporting process. There's a massive difference between explicit and implicit modeling. And we need to keep reminding ourselves that implicit modeling is just different. Okay, and so the tools that we have at hand are somewhat different to what we are used to from our often CAD-based software. So let's talk a little bit more about the implicit modeling and what Leapfrog Geo actually uses in the background in order to make it all work. The RBF technology, I'm going to tell you a little bit about it, and the mathematical function that underlies the implicit modeling. I'm not going to talk too much about math here at all, but just to give you an impression of what's going on. So Sequent, formerly Arans, developed the fast radial basis function, or fast RBF, that is designed for surface and volume modeling from point and interval data. It is akin to dual kriging and ideal for describing irregular, non-uniformly sampled data, i.e. geology. So this is exactly what we're dealing with on a regular basis in the field. And just imagine the following, just as an example. You're sampling a beautiful outcrop and you collect lots and lots of valuable data, but your next sample is located several hundred meters or even kilometers away, or separated by a sheer cliff or swamp, whatever you will have it. So what happens is that you have indeed irregularly non-uniformly sampled data. So your data points are unevenly spread. And on top of that, not every outcrop, of course, provides the same level of information. So now we apply our geological expertise to make decisions on the likely connectivity of data. So we take all of this information and we sort of, try to interpret what's going on in the spaces in between. We can use for this a pure statistical approach to start with in Leapfrog Geo that uses a mathematical function. And how does this work? Well, basically, the program identifies something very specific. I'll show you just right here, these little green points, and these points here are contact points, okay? So what happens here is these contact points can be derived, let's say, from interval data. It could be derived from just literally XYZ information being introduced, and Leapfrog takes these points into account and labels them 0. Now, the inside of a lithological unit is defined by a positive value away from this 0 points, shown here in red. And it identifies a negative distance away, or the outside of a volume, by introducing here these blue points, okay? So this is the negative distance away. And by placing these particular information on the inside and the outside relative to each other and weighing the information in a kriging fashion, the surface is built in between in an area that has a statistical likelihood of best fit, basically. Okay. Of course, this is just the starting point for your modeling process. Okay, so this provides the base layer, and it's really up to you to then tell the mathematical engine that, for example, a kink in your data set is not natural, let's say. That, for example, a fault occurs there. So it's really up to you to then put on top of this base layer information your level of interpretation, your geological expertise, and you can do that. Okay, so I'm going to provide you with all the tools today and how you can modify a surface once the RBF has created your base layer. So trust me when I say at this point, computers are not going to take your jobs away. You still have to do quite a bit of work to create a model that is appropriate for your geology. Okay, so let's keep on going. Now, what common surface issues do we usually face? Of course, depending on the distribution as well as the scarcity or abundance of data in certain areas, some mathematically defined surfaces can look a bit odd or may represent some issues that are inherent to the way the calculations are run. So in today's demo, we will learn how to deal with different scenarios by providing insight into the way the implicit engine thinks, basically. And what common problems do we encounter? So, for example, intervals aren't being incorporated into the correct surface, or surfaces are not honoring specific input data. Surfaces could be too blobby or bulbous, or surfaces are not far enough, or they might be in some form disconnected. For each of these particular issues today, we're going to provide an example and a solution. And the editing options that I'm going to present are how to adjust the surface resolution and snap to data. I'll explain the concept of intrusion category compositing, define the idea of volume points and generation, and we'll talk about value clipping and the application of global trends or structural trends, as well as the setting of boundary filters. And then as a final step, we're going to apply additional data. So what you usually would start with at the beginning, we'll do at the very end, and that is to introduce extra points, lines, such as polylines, GIS lines, etc., to finalize our project. Okay, so let's jump into our active demonstration. And I'm going to start off here with Central. So this is my natural place for all of my individual versions and models. And now imagine the following scenario. So let's say you come to the office in the morning, you turn on Leapfrog Central, or you turn on Central, and you connect to your server environment, and you'll have a look. Okay, so what has happened today? So you go to the project of interest. In my case, it's this one right here. And right away, I see that my colleague Julia has worked on the model. That's wonderful. And I'll have a little look here at the events tab. It's going to give me some more information even. And I see here that Julia has left an annotation. Hi, Janina. Can you help me? I'm completely stuck and have no time to deal with this. Fantastic. That's, of course, the exact thing you want to wake up to. But before you freak out, always remember you're dealing with Leapfrog. So can calm down. We have this. We got this. We can handle any scenario. It will be fine. So let's have a look what the actual issue is. So within Central here, Julia actually left me an annotation with a specific location for the problem. So I can just click here on Show in Scene, and automatically now Central connects to my server and pulls down the scene view of the model and a specific geo tag here that shows me where the issue occurs. And I can see here right away, okay, this particular unit here, and I'm just going to turn on, actually you can see them here, in the light green, we've got also the drill holes. Now, this unit here really expands quite a fair bit beyond where the local drilling is. So it's quite bulbous, it's really volumetrically too large, and it's quite clunky. In addition to that, it also doesn't quite honor a whole number of different intercepts here, which really is a concern. So, okay, let's have a look at this. Maybe I can help Julia right away on the spot. So what I'm going to do now is, now that I have identified the issue and I know the version that I need to be dealing with, that's what Central is fantastic for, so I know where the problem has occurred at a specific point in time, I can now hop over to Leapfrog Geo. Here we go. I connect to my same server here. I'm going to go to my project. Here we go. And now we see in Geo the exact same history here. And of course, also on the right side here, the annotation that identifies the issue at hand. Okay. I can also go ahead now and click on that thumbnail once more to open up my scene view and load all the objects related to it. And there we go. Here is my problem. Okay. So I'm also going to bring in here the Earlydiorite so we can see the issue at hand. Now that I'm here in Leapfrog Geo, I can go ahead and now create my modifications and help Julia out. Okay. Later on, when I'm finished, I'm going to bring my whole model back into Leapfrog Central so that she can have a look at it to wherever she is, whether she's in head office right now or traveling, etc. She can download the final result. So, when dealing with any form of geological model, when we're starting creating a lithological model, a lot of the time people don't realize that there are a couple of basic setups that we need to consider before running everything, before building our surfaces. Some base information that needs to be set in the lithological model setup. If I double click here on Litho Model, I have my initial general dialog available to me. And the first thing I'd like to talk about today is surface resolution. Okay, so surface resolution here, or this number here, is to start with automatically collected or identified by Leapfrog Geo. And this number tends to be quite large relative to the spread of your data in your system. So the number that we see here is a distance number, and it depends on the unit that you're currently using for your project. So let's say, for example, this project is set in meters. So we have now a surface resolution of 100 meters, which means that the triangles that form all of my subsequent surfaces in this lithological models have a general size or length of each side of 100 meters. Okay. Now, this number here automatically could be reduced to a magnitude less if you wish. That usually should still be quite sufficient for your general processing time. Of course, it's going to lengthen your processing time the smaller your triangles are. But there are a couple of other things to consider on top of processing time, of course. Now, my triangles here are the individual components that allow my surface to snap or to touch certain contact points within my interval drilling here, for example. So if my triangles are extremely large or larger than my relative drill distance, for example, then they will have a pretty hard time to bend backwards to grab individual contact points. So when creating a triangle, always make sure that you choose a number here that is appropriate for the spacing of your contact points. So something that fits neatly in between, always maybe, let's say, half of your drill grit distance. That's a good number to start with. And then, of course, you can make some individual modifications as well. So let's say here, if I apply 10 and click OK, now this number here is then being universally applied to all of the subsequent surfaces within my surface chronology. Okay. Now, my surface, all my surfaces will rerun. It takes, of course, a little moment because now my triangles here have a lot more room to identify what statistically happens between individual contact points, between intervals here, and they will define a surface that's much smoother and much smaller. So, for example, if I just turn off my smoothing here for my Earlydiorite and zoom in, you see here that my triangles are a lot smaller now and have much more of an opportunity to capture individual contact points. Okay. Now, I can, of course, go ahead now and add another level of information or another level of resolution distinction, and that refers to individual surfaces such as the vein here, for example. Now, if you happen to have a lithological unit that is naturally a lot smaller or thinner, for example, than your general drill grid, then of course you'll have to go ahead and make sure that the triangles fit that particular unit or that particular purpose, right? So you can go to your individual surfaces under surface chronology, in this case here, the Dayside dike. You can double click on any of these here, okay? And under the surfacing tab, you have the option to make a individualized choice on what that resolution should look like. So here, surface resolution is now not inherited from the geological model anymore, but can be identified individually. So let's say, for example, I run this on 5 meters and click OK. Then my overall vein here has much more of an opportunity to really honor in the thinner areas, here, for example, my individual contact points. Okay. So these are considerations from the very beginning, and often this solves a whole lot of different issues that I might have run into. So just try to build a surface that actually has the physical opportunity to capture the data and doesn't have to bend backwards in order to grab your individual contact points. Okay. Let's go from here. Now we can continue, and this is the lovely thing about Leapfrog Geo as well. While things are running, you can actually continue working with other components. Now, something we haven't talked about yet, which is also a general setup for a lithological model, is the function for snapping. Now, snapping is something that is by default turned off at the very beginning. Now, coming from the explicit world, you may not be happy about that, but there is a particular reason why snapping, i.e. capturing every single contact point by force, basically, is turned off. Now, your surface here is created on a statistical calculation of or general weighting of all of your data points within. Okay. Now, if you happen to have distinct outliers in your data set, they might, when you rigorously snap, force your surface into areas that just don't make sense, for example. Okay. Now, if you leave the snapping off to start with, give the statistics the opportunity to look at the whole data set first and sort of naturally filter out some of the outliers in your data set. The surface will still try to trend towards them because they're still part of your data set. But if they're really, really far away, for example, let's say a couple hundred meters, which just doesn't really make sense looking at the remainder of the data, then the surface will just trend towards it, but not capture that data point. When you see something like that happening, you can then zoom into that particular area, for example, and then make a decision. Does it make sense to snap to that data point? Do I want to build a data bridge to go over there, for example? What is happening there? Is there a fault in between? Or is it really a point that is just mislogged, for example? Okay, so by turning the snapping field off to start with, you actually have an opportunity to identify whether there are potential issues in your data set or whether there is a structural problem. Okay. Of course, you can go ahead and you can turn snapping on. That's no problem at all. And you can also set up individual snapping. So for example, if I click on cancel here, again, I can just go back here into my, let's say my Dayside dike here, for example, go to surfacing, and under the surfacing tab for any of my surfaces I can create under surface chronology, I can go ahead and I can choose from the drop-down menu here from snap to data, what data I want to specifically snap to. So you can choose, for example, all data. So that could be drilling, it could be GIS information, polylines, etc. Anything that informs your model, or it could be drilling only, or even a customized setup. So under custom here, once you've clicked that on, you can then navigate to inputs, and you can decide specifically what you want to snap to. So you can literally just tick on the box, so to speak. Okay, so some levels of interpretation information, for example, might be more reliable than others. So let's say, for example, if you have very distinct and clear mapping on the surface, you might want to go ahead and really rigorously snap to your GIS lines if you really trust your data points there. But let's say, for example, somebody is giving you a bunch of polylines, maybe coming from a section. Maybe you want to start off with not necessarily snapping to them, or you have to snap to them rigorously, like in a vein environment, for example. So you really have the option here to customize your setup. And it happens once more under Snap to Data, Custom, and then choose your specific inputs. Okay. Now, let's focus a little bit on the Earlydiorite, which is really the elephant in the room here. Okay, so I'm just going to turn this, the diorite off, on, and the Dayside off. And I'm just going to hop here into my drill holes. I'm just going to make them a little bit more visible to you. There we go. And I'm also going to edit the colors here, turn off the Dayside dike, and I'm going to turn on the basement and the intermineral diorite here. And the reason that I've turned these particular intervals on is the following. Now, my Earlydiorite here, if I open up the trail of how it's been created, okay, and just as a reminder for everyone, if you ever want to learn just exactly what information has gone into building your surface, open up the black triangles and you can naturally go back all the way to the base. Okay, so this is the hyperlink that leads you back to the base information, in that case, your drill hole data. And then based on that, you choose your interval information of interest. Okay, you can double click here and that opens up this dialog box. And within here, you choose the lithologies that define this particular surface. Now, what happens here is my interior lithology is the Earlydiorite, and my exterior lithology, so the lithology that is older, that was intruded by the interior diorite, is my basement and the intermineral diorite. So this is one of the reasons why I've turned these on here on my drill traces. Based on this information here, Leapfrog will then define just exactly which contact points will be pulled from the intervals, so what to ignore and what to regard. And then based on the points, the final surface is being built. Okay. All right. So now that we have here our Earlydiorite, let's see what issues we can discern here. Now, one of the glaring ones here is the fact that we have a couple of intervals here, fairly small intervals on the side of our unit that are not being incorporated into the larger surface. So they're being ignored. Okay. We're also forming some very interesting little bubbles on the outside and the inside. So for example, there are these little green bubbles that we can see here. And the reason that we find these particular features here is that automatically when we create an intrusion surface, a form of compositing is being applied to us, or is being applied to this particular surface. Okay. So if I double click here, either on Earlydiorite points or the intervals, this opens up the dialog that we saw just a minute ago. And on this dialog here, we can see compositing. Now, under the compositing tab, we have the option to simplify our geology by filtering short segments. Okay, this is what happens automatically here. Okay, so you can turn this option on or off, but it's worthwhile considering a filtering. And it really depends on the scale that you want to apply and of course the type of unit that you're dealing with. So for example, in an intrusion scenario such as this here, we are dealing with a volumetrically rather large unit. And within the unit itself, we've got intervals here that are really several hundred meters long. Every now and then on the outside here, we've got tiny little intervals, and relative to the overall scale of this particular deposit here and this unit, they might not necessarily be of relevance. Okay, so you can filter them out, and that would be the function here, filter interior segments shorter than. Now, interior doesn't refer to what's currently within the surface. I'm just going to turn that off so not to get confused. What interior refers to is what I mentioned a moment ago. Under lithology, interior is that green unit, these particular intervals that are being regarded. Okay. Relative to that, under compositing here, we can also filter exterior segments, and the exterior segments are the basement and the intermineral diorite, and the combination of these interior and exterior intervals that are being considered here make up our overall surface. So under compositing, we can indeed filter, okay, and we can set our own distance here, our own size. So filter interior segment shorter than 2.5 meters. Let's say I'm happy with that, that's fine. But what to do with these exterior segments, and why would we filter those? Well, let's turn on the surface again, and I'm just going to highlight once more the availability of the presence of these little bubbles here. Okay. Now, what these refer to here are basically xenolith. So if I make my surface here a little bit more transparent, there we go, you'll notice that these little bubbles form a surface around an exterior interval, okay, that is longer than 2.5 meters. So basically, this has to be regarded. It sits within the surface itself, but it cannot be ignored. So a contact point is being built between the green and the brown, basically, the interior and the exterior interval. And so a surface will have to be created around it. Now, xenoliths can be very important, particularly if they reach a certain size or if they are the mineralized feature in your model, but that's a different story. But if you wanted to remove them, or if you wanted to remove anything that is a certain size that's not relative to the scale that you need, you could go ahead and you can change this number here, and I'm just going to make a dramatic change to show you the difference, and click OK. And basically what happens now is that my surface reruns the interpretation or these particular intervals here. And wherever it finds a segment that is shorter now, on exterior segment, shorter than 50 meters, it will ignore that segment. And you'll see here, indeed, this segment is now ignored, so is this, and no surface is being built around it. Of course, always remember that this does not just apply to the exterior segments here within that current surface, it applies to all of them. So it has nothing to do with that final surface. It applies to all of the intervals here. And so if you wanted to get rid of just one particular unit here, for example, you need to make sure that you apply a different method. So for example, you could click on here, move to open WP lith, and then it will point out this particular interval, and you can go ahead and maybe just ignore it in your Joho database. So there are a number of different ways on how to deal with it. You could also interval select, of course, ahead of time and then make a different selection from which to build from. It's entirely up to you how you want to deal with it, but this is certainly an option too, particularly when you deal with a large scale project and you have to apply some more universal rules. Okay, so I'm just going to go back and I'm just going to turn this back to 2.5. There we go. Okay. The next thing I'd like to talk about is, I should also mention actually, this idea of compositing also applies to deposit surfaces and any other flat surface. So erosion surfaces as well. So the idea here is that if you happen to have, let's say, a large sedimentary package, for example, you can go ahead and you can filter out tiny little segments that sort of distract from the overall scale, from the overall large package unit. So that's a possibility too. Okay, on to the next. I'm just going to make these drill holes invisible here. I'm also going to get rid of my geotag. And I'm going to introduce now these points. Now, the points that we see here refer to the exterior, interior, and contact points that are being pulled from the interval information that we've picked earlier. So let me just show you what this means. I briefly talked about it when we discussed our RBF function. And the principal idea is that Leapfrog goes ahead, it finds all of the contact points, defines them as 0, and then creates a point or volume point away from that particular 0 point, and which is then being regarded either as a positive value, i.e. a value that defines the inside of a volume, or a negative value, which is the outside. So it builds inherent polarity. Now, why do we talk about these points? Now, these points can actually be manipulated. Okay, so I'm just going to increase that surface here again. You'll see here that, for example, in the area where we have this large bulbous section, okay, we have a whole number of positive volume points here that are not constrained by any negative points on the outside. So when Leapfrog or when the algorithm looks at these points here, it sees, oh, okay, there's lots of coherency here in this particular data set. Why wouldn't it continue on? There aren't any negative constraints on the outside. There's a statistical reality here that there is a possibility for this to push out in that direction. But now we as the geologist, of course, can look at this and say, hey, yeah, this is not really how it works. I know there's a regional fabric, for example. This intrusion is actually a little bit more of a sort of dike-like intrusion. It's like it is a sheet, and it shouldn't really look like this. It should go into this direction here, a long strike here, which I can see from my drilling, and that was one of the reasons I drilled that way. Okay, so we need to tell our mathematical engine that that's what it needs to regard. And we can do this by going to our Earlydiorite surface, double-clicking here, and choosing under surfacing the additional options button. Now, under additional options here, you can choose to change a number of different features, but we're going to focus here on the value clipping function. Now, I'm going to give you a little bit of an example what this refers to. So these are all the points that are represented in the histogram. Okay, so positive on the, well, the red ones on the positive side. Then we've got our 0 values here in the middle, and then we've got our negative values here. Okay, at the moment there's an automatic clipping applied, which puts them into a relative balance to each other in terms of weighting. Okay, now what we can do is we can give each of these groups, positive or negative, a relative increased value. Okay, so for example, if this particular surface here was a balloon, what would happen if I were to blow up the balloon, or if I were to put more emphasis on the pressure on the inside? Okay, so increase the pressure from the inside out. So let's say I'm going to give more of an emphasis on the positive. Well, in that case, my balloon would increase, so it would become bigger. The opposite would happen if I were to produce more of a pressure from the outside. So if I would give my negative pressure here, or my negative points, more of an influence over the positive, then my balloon would become smaller. And this is exactly what this can control here. Okay, so if I turn off automatic clipping, I can go ahead now and let's start with a scenario 1 where my positive values are stronger than my negative. So I can give my negative bound or my lower bound here a smaller number, let's say 5, for example. Okay. Oh, makes it really small. Let's see, -5. There you go. And now we have a great discrepancy here. So the positive is much stronger than the negative. And now if I click OK, my surface has to take this new balance into account. And it's going to recreate the surface knowing that the positive is much stronger. So it has much more opportunity sort of to give the positive values here more weighting. And indeed, it creates a surface that is much more coherent and that is much more connected in certain areas and extends out now and creates a massive root zone here too. It could suddenly turn into, well, a breccia pipe, for example. Okay. Now, the opposite can be created, of course, if I go now back to Earlydiorite, value clipping. I can come back to my original values by clicking on automatic clipping again. And then I can go ahead and I can give the negative a higher value over the positive and see the exact opposite occurring. So now my surface has to take into consideration a greater weighting towards the negative, and my surface has to basically pull in. Okay. So what happens is that still all of the contact points are consistently being honored, but the surface itself is being pushed and pulled by the points on the outside and the inside. Okay, so now we have a much more coherent a feature that is pulled in the bottom here. Okay, and by pulling in, it also went ahead and it actually follows the overall strike orientation of this data set much more strongly. Okay. So you can see already the possibilities here just by playing with those particular values and creating a whole number of different shapes that might actually fit your scenario much better. Okay, let's go back to the original values. There we go. And now we're going to apply a different technique that will also help to pull our surface more into a different direction. And that refers to the application of trends. Now, we all know that when we have a trend available, or when there's a trend in our data set, we have two options. We can either apply a global trend, i.e. like a straight up planar trend to our data set that will then force our data set to take that orientation into account, or we can create a folded structural trend, for example. I'm just going to go and I'm going to build us a structural trend today, just to remind everyone how that works. Okay, so I'm going to go ahead and under structural modeling, I'm going to build a structural trend here, and it is going to be built from a mesh that I've already pre-created. That's the Earlydiorite trend here, which really picks up on the general folding here that occurred in this diorite. Okay, so it picks up on the overall strike here and the fold in between. So if I right click here, I can create a new structural trend. And now what I'm going to do is I'm going to apply a trend that is strongest along the output or input. That is exactly this mesh here, which makes sense. We want to be strong along here. I'm going to add this mesh in. There we go. And now I can also define the strength and the range of my particular structural trend. I'm not going to talk about this in much detail today, but these values are appropriate. And now we have a structural trend formed, so I can turn this mesh off. We can have a look at it too. There we go. This is our force field, so to speak. Okay, and this information can now be applied to the surface as well. So I can click here on the Earlydiorite. And now under trend, I can choose to apply a structural trend. And when I do that and apply a structural trend, I also have to change in the interpolance setting, my setting to spheroidal. There we go. Click OK. And now when we apply the trend, this surface here has to take the overall fold, this fold, and the general range of my force field into account. Okay, and the surface is being rebuilt, taking it into account. It actually matches quite nicely here. And by being forced along that particular axis here, it will also have to consider the contact points, my positive volume points and my negative volume points in a completely different light, in the light of the general trend orientation. Okay, so this is going to come in just a second. We can have a look at the final results. I'm just going to bring this back in. And here we go. So it's much more constrained, specific to the folding that has been identified. And it really pulls in neatly where we have the intercepts now. So this is a fantastic tool, in addition, of course, to everything else. Okay. Now, I'm going to jump now from the trends option over back to our dike. So here's the Dayside. I'm just going to make my trend and my Earlydiorite invisible. So I'm just going to turn this back on. And I can click here on Edit Colors. There we go, and turn on the Dayside dike. Now, for our Dayside here, we do actually have added information that we now want to introduce into our existing model. And in this case here, we've got a footwall dike and a hanging wall dike GIS line that has been mapped on surface. Okay, if we want to introduce this information here to our Dayside dike, all we have to do here is right-click on the specific hanging wall or footwall and add information. And it's basically the same idea for all of the surfaces we can build under surface chronology. You can go ahead and at any given time, you can add information to it or actively edit with the polyline. So you can add points, GIS vector data, polylines, etc. Now in this case here, I'm going to add GIS vector information, the ones that I'm just visualizing right here on topography. And here we've got the hanging wall, so I'm going to start with that. And then for the footwall, I'm going to do the same thing, add GIS vector data, and here we go. And so my vein or my dike has now to rerun, taking this information perfectly into account. It's going to take a minute to run, but this is basically the point now where you can start adding additional information. Same thing with the Earlydiorite. You could have started adding polylines now once you exhaust all of your other opportunities or tools within the implicit modeling engine. Okay, while this is running, I also like to start talking about another option here. Let's say, for example, you have a faulted model, okay? And in a faulted model scenario, oh, hang on, it's coming through. Just one more moment. There we go. So now this perfectly fits, and our Dayside dike, of course, being created within the hanging wall and the footwall surfaces, now perfectly aligns to my mapped information from the top. Okay. Let's talk about the faulted model. So in this particular case here, I have a fault that sits right in between here. And let's say, for example, that our Earlydiorite, okay, that our Earlydiorite is actually, I'm just going to quickly double check. Just bear with me for one moment. I'm just going to turn this one off again. There we go, to rerun. Oh. It's okay. I'm just going to go to this whole model. Okay, so we have a fault. We're going to introduce the fault here, and I'm going to introduce it from surface. So here we've got the fault. Click OK. There we go. And now I'm going to activate the fault for our lithological model. The scenario I want to talk about is the idea that our intrusion has occurred after the faulting. Okay, so we don't want this fault to separate out two different fault blocks, or it does want to separate out two different fault blocks, but it shouldn't separate the Earlydiorite. So to start with, the Earlydiorite here is disconnected, turned into two separate features. And now if I introduce that in combination with my fault, you can have a closer look here. Okay, so there is a disconnect here. Now, how do I deal with this? How can I actually connect these over without having to start drawing polylines along this fault to pull the surface to exactly this particular contact here? You don't have to do that in the implicit modeling engine here in Leapfrog. There is one particular feature that will allow you to automatically connect these surfaces with each other by allowing each side here, each fault block, to honor the data on the other side. The way to do this is to activate your boundaries or to turn your boundaries off, so to speak, for this individual surface. So starting in fault block number 1, I'll double click here on the Earlydiorite, and under surfacing, I have the option to change my boundary filter. Now the boundary filter basically, as the name mentions, recognizes any kind of boundary. So that could be the boundary of your extent of your geological model, faults, for example, and anything else. You can customize this too, that delineates the extent of a certain area. If you turn this off, then all of those expanses all of those expanses are suddenly not being considered anymore, and data beyond can be recognized. If I do this here for both of my surfaces, and I turn the boundaries off, they have to rerun, and they now have to take the information on the other side into account. Okay, so it's going to run for a moment, but the whole idea is that you don't have to go ahead and restructure your surfaces with polylines here to capture the other side. Okay, so now this surface runs too. It will calculate its own expanse, taking the rest into account, and it will match this in a moment just perfectly. So we basically end up with the surface that we looked at initially in a faulted scenario, and here we go. So here's our coherence Earlydiorite occurring post-faulting. Okay, so these are the individual tools that I wanted to demonstrate to you today. I'm just going to also point out that if I now want to share this information with my colleague Julia, I would just hop in here into my, my central component of my project where I can see my project history, and I can now go ahead, click on my publishing button, and I can decide, okay, I'm going to introduce all of these components here for her to view. I can click next. I can even introduce my entire Leapfrog Geo project if I wish. Okay, so just to make clear, these are all of the individual components that you can visualize within the central browser. Okay, and also in terms of the meshes, download them directly in the central browser. And then I can decide on top of that if I also want to share the entire Geo project. Of course, I'm going to be kind because I want her to be able to work with this. I'm going to say yes. I can then go ahead and zip it up in a really useful fashion, and then click next. Branch it or not branch it, i.e. bring it into the same history here, or maybe even branch it off and say, hey, this is my test run. Okay, this is something that I've now created. See if you like it. Maybe run another experimental version of it, and then see if you want to introduce this information back into your master. So you have the option to really start utilizing Central to share different versions and different ideas with your colleagues. And then I can just click ahead, click next, and publish that information. I'm not going to go through the process now, but just be aware, Central is really a fantastic place where you can collaborate with your partners in order to exchange the information quickly when you need them the most.